And welcome to the second episode of How Does a Computer Work? A bottom-up explanation. In this episode, we're going to be talking about the transistor. Once again, the little graph of where we are currently. And yeah, first of all, what does a transistor do? I'm going to be explaining how a transistor works. In a more general sense, I could explain the whole thing in a physics layer, like by explaining how the atoms interact with each other. But as a person who, or as a somebody who is designing a computer chip, it doesn't really interest us here what exactly happens in a transistor. It is more interesting in us what the transistor itself does. So we're just gonna be explaining that basically and go a little bit into the history of transistors. Yeah. So here we have technically a transistor. Just a little explanation what it is. A transistor is technically just a electrical switch. So we have technically two electrical lines. This one is our gate line, it's a signal, and this one is our line where electricity goes through, or like should go through maybe. And we have like a little lever. It's more of an imaginary lever. So the concept is understood. It's working on a physical layer with no moving parts technically. So that's just how you can visualize how it's working. So what you see now is the lever or the transistor. It's currently open. There can't there can't any electricity go through because it's not closed. But if we put electricity onto the gate, our signal, the lever will close, and now electricity can flow from here to here, which is basically everything a transistor does. Of course, there's also different types of transistors. Some transistors work the other way around, where usually it's closed, but if you put electricity onto it, it will open, and and electricity won't flow anymore through it. And of course, there's also, if you have positive electricity or negative electricity on the gate, it can also switch. To that we go a bit later again, but that's all a transistor does. It's quite simple. So, of course, how did we even get to a transistor? Transistors haven't been there all the time. We started with other things, as I already showed you in the first episode of the series. The first thing was mechanical switches. You see a little picture of the patent which Zuse used for his Z1. It looks quite complicated. Technically seen, it's just some kind of levers or switches activating other levers and switches. So it's just interconnected levers and switches in a way, which form a whole computer. And those, of course, had some problems. First of all, they were quite slow. They had to physically move from one position to another position. And of course, the margins are not 100% perfect, so there's always a little bit of delay when you pull a lever for something, and you see, like, for a really big line, you see like the thing kind of moves and takes a bit of time to actually work. Of course, due to not perfect margins, they were also unreliable. Huh? Somebody who worked who works at the Technik Museum Berlin, uh, they told me that the thing, it tends over time to just clog up somewhere, just jam, and you can't use something like and you need to unjam things somewhere, and it just happens over time. Also, it requires a lot of space. The thing is quite big. Already told you the story about it not fitting through the door and not through the window either. It is really big and doesn't do that much for the size, especially compared to this thing being like a million, like my phone being like a million times faster and way smaller than the 2Z1. Yeah. And of course, since it's mechanical things moving around and grinding onto each other, it's gonna wear out over time. And another thing is the 2Z1, it tends to collect some dust, and the more dust there is inside of it, well, the more unreliable it gets because the dust helps in clogging everything up, which makes it also unreliable and contributes to the thing wearing out. Well, after that came the relay switches. The relay switches basically work now on an electrical signals. It's not anymore physical parts moving. It is just a electromagnet. We have one here. That's like the little coily thing with the wire around it. That's an electromagnet, and as soon as there's electricity going through the electromagnet, it's gonna pull down this metal tab here, which, and due to it like being shaped like this, will push this connector here onto this one and create a contact so electricity can flow like this through here. Those were now quite a bit faster and way less unreliable. So yeah, they required still a lot of space. I mean, they require way less space than the ZZ1 mechanical switches, for example. They're quite a bit smaller. A relay switch is like this big. The small ones doesn't want to display my hand now. Like really small, not that big. Like a few centimeters, a few cubic centimeters big. Not that much space. Yeah, though still, if you compare it to a transistor, it requires quite a lot of space because you have this big electromagnet that needs to be in there. Because without the electromagnet, you cannot make any contact. But still, relays, they are still used in some sorts of applications, often with like electrical, like electricity work, or like electricity in your walls or your uh, light switches. Some of them use relays if you have systems where you have several light switches doing the same light. And that might be used over a relay because this here can take a lot of electricity going through it. It's no problem for it. Though usually you hear them, they do like a clicking sound when you actuate them, like when there's electricity going through them, like it mechanically moves, so it does a click. So that's what you hear sometimes. Yeah, they are less slow and wear out less. Still, there is parts moving. It's way less movement. It's way more reliable the movement. Though it still can move out. So yeah, happens. Some people, of course, are gonna ask, what happens if something gets in between there? Of course, it's gonna be a problem. Then the switch won't work anymore. The relay, though, usually relays, at least nowadays, are like encapsulated in like a plastic hull that nothing can get in there or out. So something getting jammed in between there is really not a thing you have to worry about with relays. No, that's how a relay works and what a relay does, basically. Now we go to transistors. Here's a picture of a few of them. And yeah, transistors work electrically, basically only electrical, and do the same thing as a relay, just there's no moving parts anymore. It's on a physical layer, like atoms pulling electrons in a certain way. Not gonna explain it exactly. If you want, there is definitely from someone a video out there which explains how a transistor works exactly in a physical layer. The good thing about them, they are fast, they are very small, they don't wear out. Of course, they can still wear out, but it's more like if they heat up too much because electricity going through them too much, then they will heat up and over time technically burn out or like wear out in that way, but it is way slower than a mechanical switch. And usually, all kinds of transistors you use, they will wear out way after you already are not using them anymore because you've got something way better already or something like that. Yeah. Then of course there's different types of transistors. In computers, mostly used are MOSFET transistors. They have the one part about them that they many transistors technically the gate, like the signal that opens or closes them, gets mixed in to the electricity. But with MOSFET transistors that are called field effect transistors, they don't do that. Basically, the gate is only opening and closing, but not pushing anything through itself. So it is quite easier to work with that, and they can get quite a bit faster. There is two types. There's or four types technically, as you see here. There is N channel and P channel. N channel, P channel just tells you if the gate, the signal needs to be negative or positive electricity. And then there is two types of how the transistor works. There is one that if there's no electricity, this one on the gate, like if the gate has no electricity, the electricity from the source to the drain, that's how those parts are called, can flow through without problem. But if there's electricity on the gate, the signal, then the electricity from source to drain can't flow through anymore. And the other one is when there's no electricity on the gate, the signal, then from source to drain there is no connection, the electricity can't flow through, and when you put electricity to the gate, then your electricity can flow through. It's basically how the different transistors work, and you can just imagine there's a lot of them interconnected, working together to create different things. And now here I told you very small, showed you these ones, they are not that very small. I mean, yes, they are small, but I didn't put that in perspective yet. So that's what I'm now gonna do. Oops, I accidentally jumped over a slide in this one. Here we have a CPU with a banana for scale, and a modern CPU of about exactly the size has almost 10 billion transistors on it. Just to get a feeling, that is 10 billions of transistors of on a like really small thing that just fits on your hand easily. Just, you see, banana for scale. So, and just imagine it's a lot of interconnected transistors that work somehow together. A lot of things that can happen at the same time that can be calculated with that. The size of the transistors is on a nanometer scale nowadays. Just a few atoms big. That's just how you have to imagine that. So, really small, work as an electrical switch. That's what transistors do. And that's basically it for this episode. Nothing much more to say. You know how a transistor works. You know where they came from now, and yeah, you know how big they actually are. Like, I mean, how small they actually are, because they're really, really, really small. Now, my sources again, of course, they're in the description as well. And this video's over now. We can see each other, hopefully again in the next one, or another video I was doing. Yeah. Then, goodbye. You can click away now, yes? I hope I do not have to tell you this again, but you can really click away from the video now. There's no problem. Huh? Just click on another video or something. Doesn't even have to be my video, even though I would of course prefer it. But you can click away, watch something else. Homework to do. Like a lot. I have to program many things for university. So just click away. We are not doing anything constructive anymore. Yeah? Really. Just click on something away. You won't need to reminisce about watching the video. The video is still up. You can still just scroll back and just watch it again. Then we would be doing something constructive, at least. Yeah? Or watch another video. They also would be explaining something to you. So yeah, please just go ahead, watch something else. Yeah? Goodbye.